All right, now we have our data, and we're ready to take an examination of this data. We're ready to break it down a little bit and take a look at things. You're going to be doing this again next week, but you're going to get a little less direction on me next week. So we're going to go through this very carefully and look at things. Remember, these were those linear fits. Okay, and we're going to talk about that in just a minute. Right now, what I'm going to discuss is there is an argument amongst the scientific community, and I've heard different scientists call these sets of things different names. Results are most, let me spell it right. Results are most often what you hear these called, but some people like to call this data analysis, and I think it kind of applies to either section of science here. Some people call this drawing conclusions. I disagree with that. I don't think we're drawing conclusions at all. I think that what we're going to be doing is eventually we're going to draw a conclusion, but a conclusion has to come from somewhere else, right? We have to incorporate some other knowledge to make it a conclusion. Fit data is the other thing that you hear people call this, because we've taken like real data that we measured ourselves, quote unquote real data, right? It was from a computer program, but it's as real as we could get. And we take those points and we have now fit them to a mathematical representation here. And I like that term, I do. We are going to draw some results from this, and we're going to do some data analysis, so I feel like we're kind of doing all three. I don't really need the picture. What I need here are these mathematical representations. So I said these are a fit, and they are a linear fit. So you have to remember all the way back, oh my goodness, all the way back to algebra, where we talked about the equation for a line. A line, if you remember, always has the same general equation, a straight line, I should say. Y equals m times x plus b. And we know we can remember, maybe not in the most pleasant of circumstances, you remember if you've got a graph here and you've got a graph of a line that looks like that, y equals mx plus b, well, the y part is just that, the fact that this is the y-axis, right? And the x part is that this is the x-axis. So m is slope, and it means a lot of different things, right? Some of you may remember it's rise over run, so it's delta y over delta x, or change in y over change in x, or it's also the rate of change, right? So if you remember any of those things from math, right, this is the application of that. B is the y-intercept, and in chemistry, the y-intercept isn't the best thing for us. We don't really care about the y-intercept. But to remember m, the slope, is how slanted this line is. And b is right here where it crosses the y-axis. We don't really concern ourselves with b. We are way more interested in m, in slope in chemistry, because we're always interested in that change. And most scientists, b is just a 0 point. It's just where we started off. So here, right, delta T for sucrose, this is m times x plus b. We have an m here, we have an m here, and we have an m here. So we can compare those slopes to one another, and we're going to see if there's something in that data, all right? So to do that, we are going to write down the m of sucrose. I'm going to abbreviate sucrose. We're going to write the m of NaCl, and by that I mean sodium chloride. And we're going to write the m of Cacl, or Cacl2, calcium chloride, all right? And what are those slopes? Well, sucrose is 0.0149. NaCl is 0.175. And calcium chloride is 0.138. Pretty sure that's a 38. Your data might be slightly different. That's okay. You should do this with your data when you get a chance. In science, it is not correct to just write a number down. A number means absolutely nothing to me, right? I need for it to be data. It's not just a number. It also has to have a unit of measurement with it. Let me fix my camera a little bit here. I think I might have jostled it loose there a little bit. Oh, well. Come on. All right, there we go. Sorry about that. If I edited these videos, I'd edit that part out. But, you know, I don't edit them. Anyways, we can't just write down a number. We need to have units on there. So the key to units is back up here in this equation that we wrote for slope is to remember it's y over x. So all we need to know is what were our units of y. Well, that was Celsius. And our units of x were grams. So I'm going to put this is degrees Celsius per grams. Degrees Celsius per grams. Degrees Celsius per grams. And these numbers look vastly different from one another. It's really hard to look at those and try and find any kind of pattern. So this is where the data analysis part comes in for us. We're going to look at those numbers and see if there's something we can do to them to make them make sense, to make them have meaning, right? Because otherwise it's just numbers that we just put down. They don't mean anything. Don't tell a math teacher that numbers don't mean anything, though. They don't like to hear that. So we're going to make it real, and the way we're going to make it real is we're going to do a little bit of factor label. And you can probably already guess what factor label we're going to look at. Delta T in degrees C is fine. We haven't really talked much about temperature. We're not going to change that. But that grams, I don't like grams. Ever since we came back from fall break, we ain't done nothing with grams. You can't compare grams of sucrose to grams of sodium chloride. What I can compare it to, though, is moles. So we're going to go from delta C per grams to delta C per mole for all three of these. And this is not the first time that we've done grams to moles, I hope. And I hope you remember that to go to grams to moles, you've got to have that molar mass, right? And where do we get the molar mass? The periodic table of the elements. You got it. P tote away. All right, so hopefully you didn't lose yours. If you did lose yours, I'm going to talk about that here in just a minute. So we're going to factor label all three of these. I'm not going to do them all at the same time. We're going to do them one at a time. If I'm going from grams to moles, right, I need to know where grams is going to be in this next step. So since grams is on the bottom, it's going up top. See how factor label works like that? Even though you didn't know what you needed to do, it's going to tell you what to do. I love factor label. We got grams on one side, we got moles on the other. Anytime you got grams on one side, moles on the other, a 1 always goes in front of moles. Grams comes off the periodic table, or clearly I have searched for this before. If I Google the molar mass of sucrose, I get 342.30 is what that winds up becoming. 342. Where did that come from? That came from the periodic table of the elements for sucrose. Right? Google did that one for me. I actually think they're referring to Wikipedia, and you know somebody on Wikipedia did that for them. So now we're going to plug that into our calculator, and we get 0.0149 times 342.30. And I get 5.10. I'm just going to put 5.1. How about for NaCl? For NaCl, moles 1 mole is on the bottom. That should be a 1. And 58.44 grams per 1 mole. Again, that came off the periodic table. I also happen to have that one memorized because we use that one a lot. 0.175 times 58.44 gives me 10.2. Look at that. 5.1 and 10.2. In your brain, you might want to put a guess down. What do you think this third one's going to be? See if you can figure it out. Right now, I'm going to put down 1 mole on the bottom. Oops. Put 1 mole way down on the bottom. And for calcium chloride, it's 110.98 grams. 1 calcium, 2 chlorines. So 0.138 times 110.98 gives me 15.3. What? Did you guess it? Did you get it right? Did you figure out that this one is 1, this one is 2, and this one is 3? Because if I take each of these numbers and divide them by the smallest one, divide by 5.1, 5.1, sorry about that, divide by 5.1, divide by 5.1, they all come out at 1, 2, 3. Isn't that weird? Isn't that weird? And we see that for some reason, the slope of the calcium chloride line is actually 3 times the slope of the sucrose line. How weird is that? The first person to observe this was a guy by the name of Hoff. Okay? And Hoff discovered this, and so they named the phenomenon after it. This is known as the Hoff Factor. And what it basically, the base idea here is, which thing I put into water drastically changes the properties of that water. It's kind of neat. And we're going to talk about where that comes from in the next video.